Hey everyone, in this video we are going to learn how to simplify square roots. Starting off with a few definitions, the symbol we use is called a radical sign. You can see that right here. The number inside the radical is called the radicand. In the example square root of 16, we can label both parts. So we have the symbol, which is the radical, and then the 16, which is the radicand. If we were to simplify this, we need to understand that a square root is a number that, when multiplied by itself, equals the number inside the radical. So, evaluating or simplifying this example, square root of 16, our thought process is to find a number, when multiplied by itself, that is equal to 16. We're essentially finding a factor pair where the factors are the same. In this case, we can say the square root of 16 is equal to 4, since 4 times 4 is equal to 16. Some of us may have thought about negative 4 here, since negative 4 times negative 4 is also positive 16. But when we use the radical sign, we are referring to the principal square root, which is always the positive square root of a number. So this simplifies things for us. When we're evaluating or simplifying a square root expression, we are only looking for the positive factor that multiplies by itself that is equal to the radicand. Now this is the process when the radicand is a perfect square. What happens when the radicand is not a perfect square? And that's what we explore and learn how to do in the next few slides. First off, recall from properties of exponents that the quantity AB raised to the second power is equal to a squared times b squared. We're able to take each part of the expression inside and raise it separately to the second power. In the same way, radicals follow this rule, where we can take the square root of AB and expand it as the square root of A times the square root of B. So the product of two separate square roots of A and B respectively. The reason this works is because square roots can be thought of as exponents. In particular, they would be raised to the 1/2 power. Fractional exponents go beyond the scope of this course, but they are a really interesting topic if you wanted to look further into them. For our purposes here, we need to understand that a square root really is an exponent, and we can carry one of our properties of exponents through. This is going to help us simplify square root expressions. If we look at the bottom, for example, we have the square root of 32. So 32 is our radicand. It is not a perfect square. So the process we start going through is to find a factor pair of 32 where one of the factors is a perfect square. So here we can see the factor pair that is used is 16 and 2. 16 is a perfect square. Then we use the property that we wrote out right here, that the square root of a times b is equal to the square root of a times the square root of b, to get square root of 16 times square root of 2. And this allows us to simplify the square root of the perfect square, as we just did in the previous slide. And then the other square root term, in this case the square root of 2, stays. So we get 4 square root of 2. This is what we consider a simplified version of the square root of 32. So in order to simplify square root expressions, we are going to need to do some factoring and also incorporate work with perfect squares, right? And make sure we know our perfect squares to help us along. So writing this all out, in order to simplify a square root expression, find the largest, and that's important to note, the largest perfect square which will divide evenly into the radicand. Use this value to rewrite the radicand as the product of two factors, simplifying the square root of the perfect square factor. Okay, so this is, in words, what we spoke about on the previous slide. You can see a list of the first 15 perfect squares, always nice to reference. Never going to use 1, since that doesn't change the number inside the radicand. Okay, but 4, 9, 16, those are the numbers that we are going to try to use as part of the factor pair. So our next example, square root of 80, we're going to take from the beginning. So we want to come up with a factor pair of the square root of 80, or of 80 rather, where one of those factors is a perfect square. Okay, so if we go through our list, the first perfect square that we would try is 4. So 4 times 20, that does work, okay? And we can simplify 80 with the 4 and the 20. But remember, our goal is to find the largest perfect square. So 4 times 20 is a great factor pair, but let's see if we can find a factor pair with a larger perfect square. So next we check 9. 9 does not divide evenly into 80, so we move on. And then we get 16. 16 does divide evenly into 80. The other part of that factor pair would be 5. So 16 is a larger perfect square, so we're going to choose that as our factor pair, 16 and 5. So we get square root of 16 times 5. Then we use the property we stated before, so we can separate this to the product of two separate square roots. And then we can simplify the square root of the perfect square factor to get 4 square root of 5. Now, I want to backtrack a minute and go back to that factor pair of 4 and 20. Let's suppose we found 4 times 20 as our factor pair and we went with that. Could we still get the right answer? Okay, so we have 4 times 20 now. Okay, so we use our property, square root of 4 times the square root of 20, and we get 2 square root of 20. Clearly, these two answers are not the same, but if we focus in on the 20 for a moment, 20 can be simplified further because 20 has a factor that is a perfect square. So if we redo the process one more time, so now we have 2 times the square root of 4 times 5, 2 times the square root of 4 times the square root of 5, and then we would have 2 times 2 times the square root of 5, which would equal 4 square root of 5. Now notice the answers are the same. That is a nice result because that means that we don't have to get the largest perfect square factor right away. We could start with a perfect square factor that is smaller. We would just have to repeat the process maybe once, maybe twice, maybe 3 times in a certain situation in order to get the most simplified answer possible. Now, one way that we can help ourselves here to find the largest perfect square factor is, instead of working up the list of perfect squares, try to find a starting point somewhere in the middle and work down. So the way that works, if we think about here, the smallest factor of 80 that's possible is 2, right? Splitting a number in half. So if you think about 80 written as 2 times another factor, it would be 40. And essentially, the 40 gives us our starting point in the list. We would go to our list of perfect squares. 40 falls somewhere right in between 36 and 49. And what we'd want to do then is work our way down the list of perfect squares, starting at the largest possible and then moving down. So we would try and see if 36 divides into 80 nicely, and then 25, and then 16. That strategy is nice because we will find the largest perfect square as we go through. So this is just another way to think of it. The first way we broke this problem down, we worked up our list of perfect squares, and now I'm offering you an approach where you find a different starting point in our list and work your way down. And that's the way that I'll move into our practice. A squared expression is in simplest form when? So how do we know we are done simplifying? Well, no radicands are divisible by perfect square factors other than 1. No radicands contain fractions. No square roots appear in the denominator of a fraction. So let's put some examples here just to make sense of it. So if we have something like the square root of, let's say, 24. Right? Question is, are there any perfect square factors of 24? The answer would be yes. So we would split it, square root of 4 times 6, and then we'd have square root of 4 times the square root of 6, and then we'd have 2 square root of 6. And then before we are confident we are done, it's just helpful to check the radicand that we get, in this case is 6, and ask yourself one more time, are there any perfect square factors of 6? We can confidently say the answer is no, and then we can say that 2 square root of 6 then is the answer in simplest form. No radicands contain fractions. Well, let's say we had something like the square root of 1/4. Well, the same way we can separate a product inside of a radical, we can do the same with a quotient or division. And what that looks like is we would take the square root of the numerator and the square root of the denominator separately. And then, in this case, both 1 and 4 are perfect squares, so then we'd have 1/2 as the simplest answer. If the numbers inside were not perfect squares, then we would have to do some of our simplifying work that we've went over. And then no square roots appear in the denominator of a fraction, so something like 1/square root of 2 is not considered to be in simplest form. Now, how we tackle this one, we're going to leave that as an open question. That's going to be addressed in a later video, and that is called rationalizing the denominator. But for now, let's focus on simplifying. So we start off square root of 121. 121 is a perfect square, so we can say that this is equal to 11. I remember that idea of the principal square root, only the positive value here. Square root of 12. Okay, so we want to find a perfect square factor of 12. So we can say this is equal to square root of 4 and 3. So we have square root of 4 times the square root of 3, 2 square root of 3. Square root of 72. So this is a number that I'm going to use the strategy of working down the perfect square list. So if we divide 72 by 2, right, in half, we would get 36. Well, that actually works out perfectly for us because 36 is a perfect square, and it's the largest perfect square that we could possibly use as a factor. So then very quickly, we can say this is 36 times 2. Square root of 36 times the square root of 2. 6 square root of 2. Now, 72 does have other perfect square factors. Suppose you tried 9. You would have had 9 times 8 as the product inside of the radical. Again, you could still get the right answer. You would just have to do the simplification one more time. The radicand of 8 could be simplified again, 4 and 2, and then you would go through that process. Okay? Square root of 54. So let's start with the dividing by 2 method. So splitting in half, we would get 27 as the other factor. 27 is not a perfect square, but it gives us a great starting point. So we're going to work down the perfect squares from 27. So the first one up would be 25. 25 is not a factor of 54, so we move down. 16 is not a factor of 54, so we move down. 9 is a factor of 54, and the way we work means 9 is the largest possible perfect square. So 9 times 6, square root of 9 times the square root of 6, 3 square root of 6. Next up we have 288, larger radicand. Let's find that starting point in the list of perfect squares. So we divide 288 in half. we get 144. That is a perfect square. It would be the largest possible perfect square. So we can write 144 times 2 as the product inside of the radical. Separate 144 times the square root of 2. And then we have 12 square root of 2 as the simplest form of square root of 288. Next up, the square root of 147. So 147 is a bit harder to factor. We'll start with our half method. So half of 147 is 73.5. And again, it's okay that there's a 0.5 there. It's just a starting point to work our way down from. So the first perfect square would be 64. That does not divide evenly into 147, so it's not a factor. And we move down. Then we try 49. 49 is a factor of 147. It'd be 49 and 3 as our factor pair. Square root of 49 times 3. We separate 49 times 3. And then we have 7 square root of 3. Next up, we have the square root of 320. So we divide it in half. So that would give us 160. 160 is not a perfect square, but it gives us a great starting point. So we try 144. That's not a factor. We move down. 121. That is not a factor. We move down. 100 is not a factor. We move down. 81 is not a factor. We move down. 64 is a factor. It would be 64 and 5 as our factor pair. So 64 times 5. So this example is a bit more challenging. 320 as a radicand is a larger number. It has more factor pairs. Okay, but we slowly work our way down. So then we get square root of 64 times the square root of 5. And then we get 8 square root of 5. Now for this example, if you had trouble finding larger factors, then start with a smaller perfect square factor. Maybe you see right away that 4 is a factor of 320. And then you break it down, 4 times 80, and now you repeat the process focused on 80, which is a little bit easier to break down as a radicand. That method is totally fine. It's just going to be a few more steps than the one we have written out here. Square root of 51. Okay, so divide 51 in half, we get 25.5. So first perfect square we try is 25. Not a factor of 51, we move down. 16, not a factor, we move down. 9, not a factor. 4, not a factor. So we've run through the list of all possible perfect squares, and none of those perfect squares are factors of square root of 51. So what do? We leave it alone. That means the square root of 51 is as simple as it can get. We cannot simplify that example any further. Square root of 175. So let's try this one a bit more directly. So instead of going through a list and finding a starting point, let's see if we can think of the perfect square factor in a more direct manner. So when I look at 175, the factor that jumps out to me would be 25. So we can say that this is the square root of 25 times 7. So square root of 25 times the square root of 7, 5 square root of 7. And if you were able to come up with a factor pair in a more direct manner, then do that. It's going to be the fastest way possible. Let's try it again with the square root of 1,300. So looking at 1,300, 100 stands out as a factor. So that would be 100 times 13. So square root of 100 times the square root of 13, 10 square root of 13. And now we have a few fractional examples. So the square root of 1 over 144. So as we pointed out earlier, we can rewrite this as the square root of the numerator over the square root of the denominator. The same way that we can break up a product inside of the radical, we can break up a quotient. And then this is going to be equal to 1 over 12, since both 1 and 144 are perfect squares. Same thing here. We can rewrite as the square root of 225 over the square root of 81. And that's going to be 15 over 9, since they are both perfect squares. So this is the skill of simplifying. We're going to carry this skill into our next few videos, which focus on operations, addition, subtraction, multiplication, division, and rationalizing. So make sure we practice this up, and I'll see you in the next video.